Question 1. Let A be an n by n non-singular matrix. Which of the following statements must be true? So before looking at any of these options, let's write out some things that we know, given that A is an n by n, and instead of non-singular, let's just write invertible matrix. Well, a matrix is only invertible if its determinant is not equal to 0, and that also implies that we can row reduce our matrix to the identity. So the row reduced echelon form of some matrix, some invertible matrix A, is the identity in n dimensions. What else? Well, I don't know if you guys use this terminology in this class, but a n by n invertible matrix, the transformation represented by that matrix is onto and one-to-one, which are just properties that result from the columns of that matrix being linearly independent, and the columns of that matrix, or sorry, the columns of that matrix spanning the output space. And what happens as a result of that is that every single input vector will have exactly one unique output vector. You won't have any overlap, and so every input vector will have a unique output vector in the output space, which is r to the n. I'm not going to write all that out, but we do know that. And then finally, because our matrix is full rank, what's the dimension of our null space? Well, if our rank is n, that rank plus our nullity, the dimension of our null space, is equal to the number of columns of our matrix, which is also n. So we can subtract n from both sides. Our nullity must be equal to 0, which implies that ax equals 0 has only the trivial solution, which means that the only solution for this will be the big 0 vector as an input. So an invertible matrix will always map the origin to the origin when it is applied as a transformation on Rn. So let's go look through these answer choices. We should have all of these figured out. The determinant of A is not equal to 0 if A is an n by n invertible matrix. Being invertible implies that your determinant is not 0. What about 2? The rank of A is equal to n. Yes, we know this has to be true. Our matrix has to be full rank, and that's also equivalent to being reducible to the identity matrix, given that our matrix is square. What about 3? Ax equals 0 has infinitely many solutions. Nope, our nullity has, the dimension of our null space is 0, which implies that our null space has only the trivial solution. So no, not infinitely many solutions. And since we had said a second ago that ax equals b, so applying the transformation to an input vector to get an output vector will always give us a unique solution for b. So yes, this is true. 2, 4, and 5 are our correct answers. So E for number 1 is correct. Question 2, consider this initial value problem with all those initial conditions, etc. Find the largest interval on which this initial value problem has a unique solution. So right out of the gate, the first thing we have to do is divide out anything that's on y double prime. So y double prime plus 1 over t times t minus 10 times y minus, sorry, that's y prime, minus 1 over t minus 3 times t minus 10 times y is equal to ln t minus 5 over t times t minus 10. Now, number line time, let's note where our initial condition is. Y at 6 is equal to 0. All we care about is that t value there. So 6 is our initial condition, and I'll box that in to make it stand out, because what the other things, that wording's terrible. The other things that we're going to note on this number line are the discontinuities in this expression here. So anytime that we get undefined behavior, we will note what value of t that occurs at. So for t is equal to 0, we will get something divided by 0 in 3 of these y expressions. And so t is equal to 0 is a discontinuity. Likewise, t is equal to 10 and t is equal to 3 also have those same bad properties. T is equal to 3, t is equal to 10. Yeah, this is definitely not drawn to scale. Okay, there we go. And then we have one more hiding in this natural log. If t is less than or equal to 5, t is equal to 5, we will have, if t is less than or equal to 5, we will have a 0 or negative number inside of this natural log, which will make it undefined. So now all we're doing here is figuring out how far we can go left from our initial condition and how far we can go right before we hit a discontinuity. And this gives us our interval, which is where we have a unique solution guaranteed to exist, which is on 5, 10. So E is our solution for number 2. Question 3, which of the following subsets S is a subspace of V? Okay, so we have V being R3 and S is the set of vectors satisfying this thing. Well, as a general rule, if you have a plane that passes through the origin, it is a subspace of R3. And why is that? Because I'm going to draw an incredibly crappy plane here, but just picture this thing passing through the origin. Since it goes through the origin, it includes the 0 vector, which is one of our rules. I'll write out our 3 rules, actually. We have to include the 0 vector. We have to be closed under 2 different conditions, scalar multiplication and vector addition. So if we take 2 vectors in a plane and add them together, we will get something else in that plane. If we take any vector in this plane and multiply it by a factor, we will still be in that plane. So yeah, this works for everything. This works for everything. If you have a plane that does not pass through the origin, though, it will not work for any of these. What about 2? We have the space M2 of all the real numbers, so that's the set of all real matrices, or real 2x2 matrices, and S is the set of 2x2 matrices with a determinant of 0. Sorry, with a determinant not equal to 0. Let's see if this will be closed under vector addition. I have a feeling that it won't. So if we have this matrix, we have that matrix right there, this has a determinant of 1, right? So this is part of our set. But what if we add it with another member of our set, and that other member of our set just happens to be -1 multiplied by that other matrix? This will give us 0, 0, 0, 0, which has the determinant of 0. So it's pretty clear that this guy right here is not closed under vector addition. And really it's matrix addition, but you know what I mean. We call the individual members of a vector space vectors no matter what they are. Okay, 3, we are dealing with the space P2, so all of the polynomials of degree at most 2, and S is the set of polynomials of this form. So this is looking pretty good to me. As long as you're dealing with linear coefficients here, so what I mean is we don't have any unknown coefficients a that are squared, or different ones that are multiplied together, you're usually pretty fine. And we can prove this because if we take some a1 and a2 that are just real numbers, and we also have a b1 and a b2 from the reals, we can add two of these guys together, and we will get, we'll add 2 members of this set together, and we get a1 plus a2 x squared minus b1 plus b2 times x. And the nice thing is, these things right here are still by definition real numbers. Nothing has really happened here. We can find another a3 and b3 that we can use to replace these 2, and it'll be just another member of our set. Likewise, we can multiply this thing by whatever constant we want. There is no constant that is a member of the reals that we can multiply by some other real numbers to get anything other than more real numbers. And since this includes the zero polynomial, because a can just be 0 and b can just be 0, this thing is a perfectly valid subspace of P2. What about 4? We have the space of real n-dimensional matrices, and S is the set of n-dimensional non-symmetric matrices. So it really doesn't matter that we're dealing with a bunch of different dimensions at once. Let's just go to n equals 2, because if we can find a counterexample for n equals 2, we don't have to care about any of the other dimensions. So non-symmetric matrices. Are there two non-symmetric matrices that we can add together to get a symmetric matrix? Well, how about this guy right here? It's not symmetric because if we put a mirror up to its main diagonal, we don't have, equal values on either side. You could also test that by taking the transpose. This transpose would be this guy right here. It's not equal to its own transpose, so it is not symmetric. Therefore, it's part of this set. And then what if we add that with just, you might have guessed it, the negative version of that first matrix, 0, -1, 0, 0. We add these together, we get 0, 0, 0, 0. What's special about the 0 matrix? It's symmetric. It's equal to its own transpose. It is a mirror image of itself down its main diagonal. And yeah, so this thing is not closed under vector addition. And where is that? So we have 1 and 3 is correct. That's A for number 3, and the answer key agrees with me. Question 4, we're finding a general solution to this equation expressed in terms of the D operator, so the derivative operator. And the nice thing about this is that we don't really have to do much work here. Usually, even in the case where we're given like y double prime plus 2y prime plus 3y is equal to 0, we still have to pull out our characteristic equation to solve, but we don't have to do any of that here. It comes pre-factored. All we really have to do is solve for d is equal to 0. And when is d equal to 0 up here? Well, a couple of these are more obvious than others. When d is equal to -1, that makes this component 0. When d is equal to 1 with a multiplicity of 2, that makes that component 0. And what about this? D equals, okay, let's do the what's it called? the quadratic formula. -b over 2 plus or minus the square root of b squared minus 4 times 2, that's -4, so 2i all divided by 2. We get -1 plus or minus I as our solution for that. So any of these solutions work, and this is just like solving our characteristic equation. So we can just replace these with r's and make our general solution like we normally would. Y of x is equal to, let's just do these one at a time, this r equals -1 will contribute to a c1 e to the -1 times x. This r1, r equals 1 with a multiplicity of 2 will give us a c2 e to the x plus c3 x e to the x. Remember, when we have multiplicities, we have to add an x on for every additional multiplicity above 1. So if this was a multiplicity of 3, we would have plus c4 x squared e to the x, but we don't, so that's useless. And then for this conjugate pair here, this will lead to plus c4 e to the -x cosine x plus c5 e to the -x sine x. And there we go. There we go. So where is that answer choice? Where is that answer choice? They're making these hard to read here. I think B. Yeah, B seems to match. Yeah, B matches everything that we have here. 4 is B. Okay, great. That's the scariest thing about these questions, picking the correct answer when you got all these pluses and minuses running around that they're trying to trick you with. Okay, we have a matrix A. We're looking for the set that it forms a basis for the column space of A. So the general way that we go about this is row reducing A, figuring out what the pivot columns of A are, and then going back up from our reduced matrix to our normal matrix and picking those reduced columns. It might be column 1, 3, and 4, and then the set of those will be a basis for the column space. So let's run through that. 1, 2, 3, 4, 5. 1, 2, 3, 2, 1. 2, 4, 0, 2, negative 2. I'm going to divide that row by 2 right off the bat. So 1, 2, 0, 1, negative 1, and 0, 0, 0, 1, 2. And we're ready to reduce this thing, but I'm going to make a copy and make this bracket a little bit nicer. Okay, row reduction time. Let's subtract row 1 from row 2. Actually, row 2 from row 1. I'm liking that better. We'll get 0, 0, 0, 2, 4. That can become 0, 0, 0, 1, 2. And we can use it to set row 4 equal to all zeros. Okay, let's subtract row 2 from row 3. We get 0, 0, negative 3, negative 1, negative 2. There, I'll flip all the signs here. Let's subtract row, actually, pause. This is one bad habit that I have. We're actually done. There is no more row reduction we need to do. If we rearrange everything, we can see right here where our pivot columns are. We have a pivot position in column 1, a pivot position in column 3, and a pivot position in column 4. I did get very lucky by circling those kind of accidentally as I was explaining the question at the very beginning. So where is that set? That is answer choice D. So those three should form a basis for the column space of A. And 5 is D. Question 6, the general solution of this equation here is what? Let's pull out our characteristic equation. That's r to the 4th minus 8r squared plus 16 is equal to 0. R squared minus 4 squared is equal to 0. This has roots. R is equal to plus or minus 2 with a multiplicity of 2. That means that when we're writing out y, they're using x here, y of x, well, we have 2, 2, negative 2, negative 2. So we will get c1 e to the 2x plus c2x e to the 2x plus c3 e to the negative 2x plus c4 x e to the negative 2x. Remember, we're adding those x's whenever we're dealing with multiplicities higher than 1. And that is answer choice A for number 6, and that's correct. Question 7, we have a matrix A here. Which of the following is a basis for the null space of A? Wow, this is just about the easiest possible matrix they could give us here. Let's row reduce it. We have 1, 1, 1, 2, 2, 2. We can subtract 2 row 1s from row 2, 0, 0, 0. And yeah, we're essentially done. We have 2 free variables here. And to get a better idea of what's going on, let's write this row equal to 0 as an equation in terms of x1, x2, x3. This says that x1 plus x2 plus x3 is equal to 0, or x1 is equal to negative x2 minus x3. So if we are making a vector out of each of our free variables here, we will have an x2 vector, and what will that look like? Well, x1 is equal to negative 1 x2. x2 is equal to 1 of itself, and it's not dependent on x3 at all because that's another free variable. Then if we're making an x3 vector, what is x1 equal to? x1 is equal to negative 1 x3. Just grabbing that from this equation here. It's not dependent on our other free variable, and it's equal to 1 of itself. And you'll see that that's a trend whenever you're making these kind of vectors here. Whatever free variable you're forming that vector from, you'll always have a 1 in the position that corresponds with, x2 in this case and x3 in that case, because they're always equal to themselves. So these are our vectors here, And that looks like answer choice A, which is correct. Question 8, let y of t be the solution to this initial value problem. We're finding y at 1. Looks like we are going to need to do some undetermined coefficients, and we're finding the entire solution, so we might as well just start off with solving our characteristic equation for yc, because our overall solution, y of t, is equal to our characteristic solution plus our particular solution. And we'll find the first half using not undetermined coefficients, just by solving our characteristic equation, which is r squared plus 3r minus 4 is equal to 0, r plus 4, r minus 1 is equal to 0, r is equal to 1 and negative 4. That means that yc is equal to c1 e to the t plus c2 e to the negative 4t. Okay, that's great, because what it means is that our guess for y particular, let's see, y particular guess as a function of t, what we would have liked that to have been, those tenses are weird, sorry, rephrase. We're finding our guess for y particular of t. If we had overlap between what that guess would have been and any of the components of yc, we would have to multiply this thing by multiples of t until we no longer had that issue. But since we don't have any e to the 2t terms in this solution here, we are perfectly fine, and our guess for y particular can be just generalized as a e to the 2t. We will need two derivatives, y prime and y double prime. This gives us 2a e to the 2t and 4a e to the 2t. Now let's plug those into this equation here for y prime, y double prime, and y. And since everything will have an e to the 2t in it when I plug it in, I'll just get rid of those entirely. So we will have 4a plus 6a minus 4a is equal to 6, dividing the e to the 2t out from there. So this tells us that 6a is equal to 6, or a is equal to 1. And because a is equal to 1, we can get rid of all this and just write our solution yp as 1 e to the t. So now finding our actual solution, y of t, it will be of the form c1 e to the t plus c2 e to the negative 4t plus e to the 2t. Now we have to apply these two initial conditions to find our values for c1 and c2, but for that we need y prime of t, that's c1 e to the t, minus 4c2 e to the minus 4t, plus 2e to the 2t. Now plugging in these initial conditions, y at 0 is equal to 2. That tells us that 2 is equal to c1 plus c2 plus 1. I'll subtract that 1 over, and we get 1 is equal to c1 plus c2. And then y prime at 0 is equal to 3. So 3 is equal to c1 minus 4c2 plus 2. Subtracting that over, we get another 1 there. So making this into a little augmented matrix, 1c1 plus 1c2 is equal to 1, and 1c1 minus 4c2 is also equal to 1. And so we can solve this. We can subtract row 1 from row 2. We get 0, negative 5, 0. We can simplify this down to a 1 and subtract it there. And if my eraser will work, there we go. We see that c1 is equal to 1, c1 is equal to 1, and c2 is equal to 0. So this right here is our solution, exactly this. And so what are we solving for? We're finding y at 1 right there, and I'm kind of writing all over the place here, but y at 1 is just e plus e squared. That's answer choice C for number 8, and it is correct. Question 9, given that y1 of t is equal to t, and is a solution to this homogeneous equation here, we're finding the second linearly independent solution y2 of t. So for this, we can apply a nifty equation for reduction of order, which says that y2 as a function of t, our second fundamental solution, is equal to y1 of t multiplied by the integral of e to the negative integral of p of t dt over y1 of t squared dt. So it's a lot to kind of take in, but eventually you can remember this one relatively easily, and we can just plug things in here, and we will have our solution. Our p of t is the same thing that our p of t is equal to in what's it called? The integrating factor. What we'll have to do is divide out anything on our highest derivative, so we get y double prime minus 1 over t y prime plus 1 over t squared y is equal to 0. This guy right here is our p of t, negative 1 over t. This integral will give us ln t, which simplifies down to just t. And since y1, we're told, is equal to t, I'll replace that here and here. This gives us 1 over t, and we get t ln t for our second linearly independent solution. That's answer choice B for number 9. Number 10, let 3 be an eigenvalue of this matrix. What is the geometric multiplicity of lambda equals 3? Well, the geometric multiplicity is the same thing as the number of eigenvectors that you get when you plug in lambda equals 3 to a minus lambda I. And what's convenient is the number of eigenvectors that you get is also equal to the number of free variables in a minus lambda I. So let's plug minus 3 in for all of our diagonal terms. What do we get? Negative 2, 2, 2, negative 1, 1, 1, and 0, 0, 0. We can use row 1 to set row 2 to all zeros, and since we have 2 free variables, then we'll get 2 eigenvectors out of this thing, and so the geometric multiplicity of lambda equals 3 is 2. That is answer choice C for number 10. Question 11, consider the mass spring system whose motion is governed by this equation right here with 2 initial conditions. Find the solution to the initial value problem. So we will need to do a pretty kind of hefty version of the solving that we did over here. We will need yc and yp because our solution y of t is just equal to our characteristic solution plus our particular solution. That characteristic solution is just gotten by solving our characteristic equation, which is r squared plus 1 is equal to 0. R is equal to plus or minus I. That means that yc is equal to c1 cosine t plus c2 sine t. And the issue here is that what we would have liked our guess to have been for our y particular is just a generalization of this 4 sine t. And remember that any constant times a sine or a cosine, that generalized for undetermined coefficients will give us a cosine t plus b sine t. But the issue here is, look, we got some overlap. The entire solution here is overlapping with things that are already in yc. That means we have to multiply each component in here by t to get rid of that overlap. Now this is not particularly fun because it means we need to take a second derivative of this whole thing. So this is going to get pretty big because we need our derivatives because we need to plug them into y and y prime up here. Sorry, y double prime. So y prime of our guess for y particular will be a cosine t plus minus at sine t plus b sine t plus bt cosine t. Y double prime will give us negative a sine t minus a sine t minus a t cosine t plus b cosine t plus b cosine t, and then finally plus or minus bt sine t. So if I've done everything correct, we should be able to combine a couple like terms here. Minus 2a sine t. Let's see, do we have any more at cosines? No, we don't. So minus a t cosine t plus 2b cosine t minus bt sine t. That's our y double prime. So let's plug that in, and we'll also plug y into this equation here, and we'll get an even bigger solution. But okay, so plugging in y double prime, I'm just going to copy this thing over. Not really feeling like writing all that out. We also have a y on our left-hand side, which is that thing right there, and that's all equal to 4 sine t. So we can equate our sine and cosine components, and also our components with t's and without t's. So let's see here. Wait, do things cancel out? I think some things will cancel out. We have an at cosine t minus at cosine t. Whoa, look at that. Both of those go away. Then we also have minus bt sine t plus bt sine t. Whoa, look at that. That's how that's supposed to work, by the way. So if that happens, you're on the right track. Okay, since we have a sine term right here and a sine term right here, the things attached to those signs must be equal to each other. So minus 2a is equal to 4. That means that a is equal to negative 2. And since we have no cosines over here, this b must be equal to 0 in order for this to be true. B is equal to 0. That means that y particular is just negative 2. And what were we using that on? Negative 2t. No, wait, this is a. A is negative 2. Yeah, so negative 2t cosine t. There we go. And since our yc was equal to c1 cosine t plus c2 sine t, we can write our overall solution, and I'm actually going to shrink all of this down so we can still be working near the top of the page. There we go. So we can write our overall solution as the sum of these two. Y of t is equal to c1 cosine t plus c2 sine t plus, minus 2t cosine t. We are told that y at 0 is equal to 2 and y prime at 0 is equal to 0. Let's find y prime of t. That's minus c1 sine t plus c2 cosine t minus 2 cosine t plus 2t sine t. And let's plug in 0 for both of those and set them equal to those initial conditions that we are given. We're given there. So 2 is equal to c1. Yep, that's all we get for that first one. And then 0 is equal to, this thing will go to 0, this thing will go to 0, and then we will get c2 minus 2. So this means that c2 is equal to 2. Okay, and that should solve everything for us. We see that c2 is 2, c1 is 2, and fingers crossed, answer choice D matches everything we got. Okay, so this kind of problem, when you have to multiply your guess for y particular by t, can end up being really, really not fun like this. But you just gotta keep going, and eventually you will make it out alive in the end. Okay, so that's the end of this exam, and yeah, it wasn't too bad. And yeah, I'm gonna go eat lunch or something now. So see ya.